Um, so let's talk about Manticore. So, like I said before, the Manticore stuff, the basic idea is that you're able to use it to do symbolic execution of a binary. And the basic idea behind that is I can take a binary, take a trace. So I have a program that's executing, and it's following a certain path through the application. And at any given point, I should be able to record what the register and memory state are. And it should be, if I start from that same register and memory state, I should be essentially the exact same path, regardless of how I started that way. What the symbolic execution is trying to do is instead of putting concrete values, so instead of doing, what's a good way to do this? So let's come in here, because what we're going to look at, we're going to look at some of these binaries again. But, so it's roughly equivalent to saying, instead of doing 1 plus 1 is, or 1 plus 2 is 3, I would do 1 plus x is 3, and I'd be able to find all the solutions for that. Symbolic execution is kind of similar in that instead of having a concrete value, what do I need to put in this register to get down this code path, it's able to use the symbolic values instead, with the end result that you're able to do some fancy solving stuff to try and calculate for a path way down this chain, what do I need as the initial input that would get me there? And it lets you do some really cool stuff. One of the better examples is that if I am fuzzing something, so let's say I'm fuzzing a really simple file format, and let's actually, is that getting clipped at the bottom there? Yeah, that looks better. So, where was I? Right. Let's come over here. Make your Manticore. And let's screen this up. So, found include standard io.h. I'm just going to put together a really simple application here, which a fuzzer is going to find very difficult, but at least in theory, a symbolic execution tool should find very easy to solve. And the easiest thing to do here is I'm going to read, so car star buff is equal to, you know what, let's do it this way even. OX 20 bytes. We want to do a read standard in. What's the right args for that? Oh, it is the right one. Standard in buff, and I want to read 20 bytes from standard in. And then int I is equal to int star buff 0. I think that works, right? Print if I is equal, that's Python. I don't want to do Python. I have to do modulus. So if I XOR 41414141 is equal to what's something good to put in here? 111111223344. That seems like a real thing. Yes. Did I mess that up? No, that's right. I want to do, well, what's the right way to cast this? I always forget how to declare a function pointer properly. So void f, void star f. Is that right? I don't know if that's right or not. Hello, Ginvale. Wow, there's a lot of people showing up today. This is exciting. But f is equal to, and this is going to break terribly, I know it. So why is my C terrible today? Okay, I missed a semicolon? I did not miss a semicolon. Oh, I did miss a semicolon. Okay, L value is required. That's what I was afraid of. Okay, let's see if I can remember how to cast this properly. Not right. Let's see what Google has to say here. Cast to function pointer. I always have to look up how to do this properly. Is that what I want? But that is basically what I put, isn't it? Oh, did I declare it wrong up here? Is that gonna work? I am terrible at this, aren't I? Yeah, the channel is really busy today. I typically don't get this many people. That's exciting. That is what I want to do. Actually, you know what? Let's just do it this way. Void win. You win. Tef, you lose. Right, so clearly the idea here is if this works, then I should be able to... I read from standard in. Why did that not buffer properly? That's not what I want at all, is it? So I'm reading from standard in. Why is that not... Printf sent x y. Implicit. Oh. Am I being dumb about this again? I'm being dumb about this. Pound include unisted.h. Much better. So standard in is 0, right? There we go. That's not quite what I want. I want that. There we go. That is what I want to see. So if I did this properly, I should be able to go python-c print. Let's actually do this. Because I find using pwn tools for this stuff so much easier than remembering how to do it off the top of my head. From pwn import star print e64 ox4141414141 XORed with ox11223344 plus b times ox1c e d e f. Yeah, that's right. So if I do Python that, not sure why that took so long. That's odd. But see, if we do this, it will print out I win, and it works. And the idea here is that if I was fuzzing for this, it would take on average about 2 billion tries, right? Because I would have to get that I value right. And in this case, that's clearly this is some magic number with a backdoor in this program. But there's all sorts of more realistic things that come up when you're trying to fuzz something. So let's say there's a CRC or there's some sort of like unlikely control flow path that we'd want to go down. And in fact, the PDF crack stuff that we were doing in the Wednesday streams is kind of an example of this. So I guess for a recap for people who haven't been watching the Wednesday streams, we spent 3 weeks trying to, so we spent a week fuzzing this application called PDF crack, which is apt search PDF crack. Basically, it's just some random PDF cracking software. Info's a thing, right? But there was a show. That's what I wanted. Yeah, so it's just a piece of software for brute forcing a encrypted PDF password. And so the first week we ran it through AFL. AFL fuzzed it for I think about a week. I spent fuzzing it. We went through and triaged a whole bunch of those results, and we found one heap overflow. Basically, we were able to manipulate. They were basically just reading a string in out of this file, putting it into the heap, and you just completely smash whatever else is there. So that was the second week, was triaging all of those. The third week was trying to do some heap grooming to get everything to line up the way we wanted it to. And then the fourth week, we started trying to actually exploit this. We'd finally overwritten some pointers. We were trying to get something useful out of that. And in the process, I stumbled across a very simple stack smash. It would read in under a very specific set of configuration options in this file. It would read in 256 bytes into a 120 byte buffer on the stack. And AFL never got down that path because the conditions to get down that path were very specific. You needed a 4-byte value in one place, a different integer value in another place, and I think you needed a third one in a third place. And for AFL to find that, it would have to line all of those up in sequence, essentially by random chance. Whereas a symbolic execution tool should say, oh, to get down this path, I need these 3 values to be a certain thing, and then come up with a way for them to be that thing. So, assuming that everything works the way that it should, if I was running AFL against this very simple application here, so we read in 32 bytes, if the first 4 bytes of it, when XORed with A's, is equal to hex 11223344, we win. Just a stupid, simple backdoor. Fuzzing this, it would take, on average, about 2 billion combinations, assuming there was no logic to break this apart or things like that. Because it would have to go through and it'd have to try each of those possible values until it found one that just by chance happened to go down this other path. On the other hand, again, let's believe there's a dash verbose flag I can use to actually print us out more stuff. Oh, this prints out way more stuff than I wanted. Never mind. I forgot that the verbose flag prints out all of the register state, and that's way too much output. But running Manticore against this, what it should do is it should run twice. Instead of the 2 billion cases that it would take to fall down here, again, on average, it should take 2 cases because it would say, oh, there's one path that takes me down this you lose path. Let's generate an input that does that. And there's a second path that will take me to the win path. And it will generate an input to do that. So, assuming that everything is working properly, the default behavior, as far as I know, for Manticore is that it will do exploration. So one thing that comes up a lot with symbolic execution tools is this idea of exploration. I should be able to say, you know what, that's a very good idea. So Mark in the chat, who's one of the developers, just mentioned that the latest version has a bunch of verbosity flags. And really, I should turn those on so that I get not only the verbosity stuff that I wanted, but also so I have all the whatever new features there are. I believe I put that in CTF tools. Is that correct? No. Where did I put this? home directory tools? Home directory tools. So I should be able to do a git pull here. Ooh. I assume being on master is decent. Do I want to use master or do I want to use one of their tagged branches? Using a tag is probably the best bet. Oh, git checkout. I'm on a tagged branch, and now... Ooh, I'm really curious. If I just... Sure, what's the worst that happens? Let's swap everything out from underneath you. And I'm sure this is going to break everything. Oh, I should be on master? Okay. I will switch to master and do the same thing. So I am positive that this is probably going to absolutely kill this test that's currently running. At least I would hope it would. So we'll do it. Oop, that's capital V. Oh wow, there's so many arguments now. Look at that. Right. So what's going on here is I have now updated to the latest version of Manticore rather than the, what is it now, 2-week-old version that I pulled down last time I did a stream on it. And so what we're seeing here is this is running through. It's doing it's doing a first pass of what exactly does this application do. And this debug output is basically saying, oh, we loaded libc, we read that in, we immapped some stuff in, we had to improtect it because it's a library. It's basically going through that startup process. And now we're waiting a little bit. And ideally, if we sit here, we wait, and we watch this run, what it's going to do is it's eventually going to get to the point where we call that read. So in the program, the first thing main does is it calls read from standard in into this buff. So what Manticore should be doing here is it should say, oh, by default, Manticore assumes that standard in is fully controlled. So it knows that it has full control of buff up to 32 bytes worth of value. It'll then see that copied into I, and then well, I guess I didn't need this anymore. It'll see it printed out, which is going to cause it to take a little bit longer than it would otherwise. But then it'll see this XOR, the comparison, and a branch. And so what it's going to do here then is it's going to actually try and figure out how to go down both of these branches, because there's both the left branch, which goes down the failure case. So thinking about branches kind of like, I think most graph-based disassembly does that. That if you're looking at them going down, the projects a.out. So the left branch over here, so we compared this against, oh, that's kind of cute. They, GCC decided to optimize the XOR out. But it's going to go down the left branch here if it does not match, or down the right branch if it does. So what Manticore should be doing here is it should say, oh, this var3c is something we can control. We need to create separate inputs to go down the left branch and the right branch and see where that gets us. So, still running, but now we're actually getting into some more useful things. Unfortunately, I suspect it's probably working pretty hard right now on this printf. We'll see. Because my guess is that, so one of the things that I was told when I was first working on this in the Manticore Slack channel is that they don't do a lot right now with trying to optimize some of these function calls. So we're calling printf with a value that we control. Let's reset. We're calling printf with a value we control, this I. What that means is that there's all of this code in libc to convert I into a hex formatted string to print out. So they're going to try and solve through all of that, plus all the branches in that, and try and come up with things like that, which isn't really what I want. I don't actually care which side of that branch you go down. Like, why on earth would I care if you printed out 4 values or 3 values? Don't care. But we can see up here that it found the right to you lose. That seems pretty solid. But we're still working on it. So we have another case for you lose. Oh no, are we going to find a whole bunch of cases for that? Core W. So we currently have 2 inputs that it's been able to calculate. So we have the first one. Ooh, I want the pickle one. I want dot standard in. Oh, I don't want state. I want test. 1.standard in. The first one is they supply a whole bunch of null bytes, and it does something. This next case, it supplies a 1 there for one of the high bits. Presumably what it's doing here is it's actually, unfortunately what I suspect it's doing right now is it's solving through that printf, which is not really what we want to do. So, let's see where we get with this. So one of the other things that's quite a bit more useful and is actually super exciting about this is I can use their API. I don't have to just say, go into this and explore. I can actually set up very specific things to tell me get where, like, I want to say that we're going to go at a specific point. I want to know what the values are such that I'm able to get down a certain path. So we wait here for a minute. What do we have right now? We got another input. 3.standard in. That looks identical to that one, doesn't it? That's odd. I wouldn't think it would do that. But ECC test.c. Don't care. Oh, I should probably give it a. Oh, we still have this open, don't we? Found include standard lib.h. ECC test.c. So we're going to start this over. You know what? I say that, and I went to all that work, and I forgot to remove. Let's try this again. So what we did here is we removed this printf, so it should be faster now, because it doesn't have to solve through all the libc stuff that was being handled with that. And while we're at it, let's reload this so we can actually take a look at the proper values here. So this looks almost identical, except that looks actually identical. What? That's not right at all. Save. Okay, that looks right. Are you caching this? No. Okay. I just don't know how to use computers, apparently. That's unfortunate. But where were we? So we should see this comparison, and we should see it, actually work. But while this is running, there's this other piece of it that's equally important. So I want to go and I want to say, rather than just exploring, I already know where I want to go. I want to get to this win path. I should be able to say, I want to get to this call. So 400.672. Open a new Manticore test.py from what's capitalization on this? From Manticore import Manticore. Im is equal to Manticore ./a.out. So we're just loading up this binary. You know what? I'm gonna bring this over so I can actually read it. Oh no. set no auto indent. There we go. So I want to then do a m.hook. And so what m.hook is doing is this is a decorator in Python. So you can have a decorator for a function. Basically what that's doing is well, let's get this all set up before I explain what that's doing. It's a little bit complicated, especially for somebody who isn't super familiar with how Python works. CPU.read int CPU.RBP minus OX34. So I'm going to print out what that value was when I get down this path. Okay, so let's explain what's going on here real quick. So we created this Manticore object. It's a class that they've defined in their library here. We've created an im, which is a Manticore class object. Then there is this decorator here. And what a decorator does is you can create a decorator, which is going to we're going to call m.hook with this argument and this function as an additional argument. So it's roughly equivalent to if we said m.hook OX400 672 comma hook as a second argument, except this is a little bit cleaner to write. Like, it's easier to read that than m.hook. Like this, it isn't quite as obvious that this is directly tied with this function definition, whereas the decorator, that very clearly is saying that this call to m.hook is directly tied to the definition of this hook function. Basically what we're doing here is we're saying when PC is equal to this value, we want to hook in to the symbolic execution using that state. Oops. CPU is equal to state.cpu. We want to get the CPU out of that state. We will then want to read an integer value. We want to read an integer value from CPU RBP minus 34 hex, which if we come back over here, that was the value that was being compared. So when we get down this win branch, oh, does a decorator? Yeah, I don't actually know how decorators work. They're kind of magic to me. I'm sure they work differently under the hood, but at least my understanding of them, which apparently is completely wrong, has got me a little ways as it is. m.hookAdder returns an object that has call. Okay, I will totally believe what disconnected says. Oh, okay. So it's not doing this, it's doing that. So not quite what I said, but kind of similar. But so that's what that's doing, and hopefully we got through this. So if we do ls-latr imcore __, we have two different paths. So there were two different inputs that it created. So we have test one.standardin. We have one that was just a whole bunch of null bytes, and then a second one that had that magic value that when we supplied it, it actually calculated that. And if we come in here, we should be able to do python t.py cat.xxd. What? Oh. Projects. That's what I get for having a lot of directories in different folders with similar names. And all open at the same time. Right, so we see that it has the first 4 bytes that are exactly the same, because that's the magic 4 bytes that we needed to get down that backdoored function. It's just that if I was fuzzing this, I would have to try all of those combinations until I got up to that, as opposed to symbolic execution, which tried 2 values, one that didn't get down that path and one that did. That's the basics of it. there's also the other side of this. So I should be able to do Manticore test.py. And what this is doing is it's very similar. It's going to do the same thing, except instead of doing blind exploration, I'm saying I want specific pieces of information. So where this would be useful is, say that I wanted, there was some comparison. So the example that I looked at to actually figure out how any of this stuff works is this multiple styles write-up by E. Hennevent, which is really great. It's actually a really useful write-up to look through. It actually shows there are two very clear different ways to do it. First, you can do the concrete solve, which is kind of what I'm doing. Well, no. So the way that the concrete solve that they're using is they're actually forcing the flag and checking what it's compared to. Because you can treat this kind of like a debugger. I can say that I want to go to right here, and I want to force the jump the other direction, and then see what the compared value was. I can't with this one because because it doesn't actually load the constant into a register. But if it did, I could read out what that register was. But the more interesting one is this symbolic solve, where they're doing something very similar. Ooh, I forgot to say solve one. Hopefully that works. Actually, not sure if this script is going to work now. And I also want to do im.. Oh, look at that. So it did a thing. What is going on here? Why can't I? What are you doing? Okay. Apparently, the combination of Vim and screen has eaten an input. That's unfortunate. Oh, I had caps lock on. That is the worst. Okay, where were we? We have this, so I should be able to say that in imcore PE. Oh, we didn't have any inputs. That's interesting. I didn't realize that it wasn't going to create those. Where's the right window? im.verbosity equal to 1. I think that's the right way to do that. We read an integer, but it didn't actually cast it quite the way that I expected it to. I thought that would work. Print. Let's see how those two work. Let's run this again. Again, if all this works the way that I think it should, then it should give me an answer here. And by upping the verbosity a little bit, it should give me a little bit more output so I can actually see what's going on rather than talking blindly as this thing runs. Although it would appear that I'm not getting as much output as I would like. I might have wanted verbosity 2 instead of 1. But essentially what this is doing is it's almost the same thing as when we were just blindly exploring. Except, instead of it just being a blind exploration, we're saying that we want to get into a certain spot and then figure things out. So, we get to. Yeah, that's the basics of it. I'm not sure exactly what, while we wait for this to run, let's think about what the next thing that I want to do is. So, what was the status on this? So, where is it? I want core. Well, this, oh. That value is symbolic. If I want concrete, I will have to solve it. That's unfortunate. So should I just do sol? state.solve1. Is that right? Yeah. State.solve1. Let's see how this works. Oh, that did not like that at all. So let's see how that works. Right. So, this is something that I was super excited about. So one thing that I'd really like to be able to do is I would like to be able to take a core dump and load it in. Because one of the problems with using symbolic execution tools, such as Manticore, is that if I'm doing something very complicated, it needs to create a way to go from the start of the application. So let's say I wanted to get down here, and for whatever reason, there's a ton of code in this first block that is super complicated to get through. But I already know how to get through. A good example is, let's say for whatever reason, I was looking at a PDF parser. Not a PDF parser. Sure, a PDF parser is a good example. So I'm looking at a PDF parser, and for whatever reason, I only want to look at one specific chunk type in there. So there's different types of chunks or sections. I don't remember what they call them in PDFs. Each of which is going to have a different function to try and process it. And let's say that I want to get into one of those paths. So one thing that I could do is I could feed in an initial file and get down that path. But based on the way that Manticore works, that may or may not be exactly what I want to do. It would still have to go through the entire first part of the program and understand how all of that works. Or, ooh, there we go. Look at that. It's done a thing. What value did you come up with? That looks like the right value with some extra bytes, because I read 64 bytes, so yeah, that looks like the right thing, doesn't it? So if we go in 3, 2, oh, that is not, 05726350. Yep, that looks like the right bytes. So we can see here, this went through and it did the exact same thing, except we directed it. So what's actually the time comparison there? Time Python Manticore test.py and time Manticore a.out. So I'm just doing this because I'm curious, not because it's going to give us anything useful. Because this, I think, is more specific, so I'd expect it to be faster, as opposed to this, which is more general. I would expect it to take longer. But I don't actually know. So, we go pop back where I was, loading a snapshot. One ability that I'd like to have is the ability to shove in, here is what memory should look like right now. Here is where to start from. Because normally it would start when, I believe it starts when the loader hands off, or prior to the loader getting loaded. That's why we saw like libc getting loaded in there. We had the debug output printing out, which realistically, there's no reason for us to have that. There's no real good reason for our symbolic execution to try and even think about loading in libraries and things like that. One of the techniques that people have used to get around that is, well, let's just take a snapshot of this thing already running. Instead of trying to go from the very start, let's start, in the middle when you're reading in my input. Or maybe even after that. After you've read it in and done the processing, I have a snapshot that says, here is where you should start. So, a feature that I would really like to have is the ability to do that with core dumps, like they already do with mini dumps. And they've had an issue open for this for a little while. It looks like it hasn't had a ton of progress, except I think me giving a thumbs up because I'd like to see this. So I don't have a lot of other stuff to talk about right now, I'm going to take a look at how this works and see what exactly that would take. Um, so where is the mini dump stuff getting done? Is that in the PE stuff? Yeah, that's in the PE stuff. So what are they doing here? I forgot. I have all this pulled down. So the Python version of this took a little over a minute and a half to run through, which isn't bad. And we're still waiting on the full exploration one. Tools, Manticore. So if I come in here, where are we? So there is a model for Windows that will do that. Okay, well, let's take a look at that. Manticore / binary / init. We've declared a class which is a mini dump. We will potentially load it in. That seems relatively straightforward. So there's this function. They've declared a class here. So for anybody that wanted to actually watch useful things they might learn something from, feel free to stop watching now, because now I'm going to poke around with some of the internals of Manticore and see how hard it would be to jam loading a core file in here, which, depending on what exactly it is you're interested in, this next part might be pretty boring. It's probably going to be a lot of me going, what is that doing? What is that doing? Oh, I guess it's doing that, isn't it? Which there's probably a decent chance isn't going to be that interesting to a lot of people. So if that's your cup of tea, feel free to keep watching. Otherwise, I'm going to take a look and explore the internals of Manticore and see where we get. So there was that in there, and there was also in the PE. So binary PE. There's also in here. Where in here was it? My phone is doing stuff. What are we doing here? So we init. Okay. Nope. I cannot switch tabs that way in Firefox, can I? Unfortunately, a little bit more complicated than I was hoping for. I guess it isn't too bad. So there's a few hundred lines to parse a mini dump, it looks like. And then whatever this code over here is doing to actually do something with it. So if we're just running this, we try and load the binary and dump out threads and maps. So here's the elf class, right? So the elf class, what do we do with that? So we are inheriting from binary, we're calling it, initing it with that.